What's happening?
I think we should go for lunch, and then everyone happy with that? And then reconvene at 1:30, and so then we'll have the two talks that we delayed, and so we'll have a slightly longer afternoon session, unless people are keen to knock them off now.
Okay, so Ben's going to kick the first half of this particular one off with electronic structure calculations of Melenins and Monomers.
Right, so this is really a talk that's first started in the ARC and this naval research in the US. The funded the work I'm going to tell you about. And just to thank the people who collaborated with this. So I split this up by theory and experiment, but after I wrote this slide, I decided that this actually wasn't really a very good way to describe the way we worked, because these two things have really been quite entangled and mixed up together. And in particular, let's look at a couple of names. It's Paul Meredith, who's the experimental group. This work's been done in very close collaboration with, and Mark Peterson, who's at the Naval Research Labs. He got me started on doing density functional theory calculations, and is involved very closely in a lot of this work. And all the calculations I'm going to talk about are used with his code, which is called NRLMOL. And I'm not really going to say very much about the code. And also Seth, who's talking immediately after me, is his work really follows on from what I'm going to talk about, and so there's really a few chapters in the same story, I guess. And I'm going to tell you a little bit about the building blocks of Melenin, and I'm going to talk about how that begins to build up into seeing the macromolecular functionality that Paul described yesterday. And these are the publications that the results I'm going to talk about are taken from. Okay, so Paul gave a long introduction to Melenins yesterday, so I'm not going to say too much other than to show a slide for my brother's wedding. So this is me, and my hair's mostly got new melanin in it. This is my brother, and his hair's mostly got clear melanin in it, and that's why he's ginger and I'm not. And this is the giant Australian cuttlefish, which has its lovely melanin ink.
Are you right at the top?
Sorry? Only rather distantly. I'll move on to the next slide. Okay, and so the other so we heard yesterday how historically the dominant paradigm to explain Melenin's macroscopic functionality has been to consider it to be a semiconductor. And this goes way back to Longview Higgins in 1960, and also the McGuinness work on switching behaviour in material. And so Bernie talked yesterday about the conductivity of melanin, and how it from his data, it no longer seems that the conductivity arises simply from electrons or holes moving around the material, but it's due to protons moving, and that protons are ambient and at higher humidities are the dominant charge carrier. And so one of the other features we'd really like to understand, if we're going to get rid of this semiconductor paradigm of melanin, is how do we get this broadband optical absorption. One thing I'd like to stress out here, 0 is not this axis, 0 is a bit higher, so it's really got quite a lot smaller over here. And this is basically exponential. And so the approach that I'm going to talk about today, we've kind of had two approaches. One is very macroscopic, and that's been involved with doing some phenomenology with the experimentalists. And the second approach we've been doing is to do some first principles calculations, and it's that latter and build up from monomers and start to stick monomers together to form diamonds, and try to understand some of the electronic structure from there. And hopefully at some point these two approaches will meet. Before I get into them, I want to make some important points about density functional theory, which will be very well known to several members of this audience, but perhaps less well known to some others. And I think this is a really important thing to appreciate. So one thing that physicists really like, and chemists seem often less enthusiastic about, at least in principle, density functional theory is exact. And so The problem is we need to know what the exchange correlation functional is, and we don't know what the exact exchange correlation functional is.
They were happy enough to give Walter Kohn a Nobel Prize.
They were quite happy with it. They just seem less taken with the exactness in my experience. So we make some approximations, and by far the most important ones are the local density approximation or generalized gradient approximations, and these various acronyms are basically different flavors of generalized gradient approximation, and all the calculations I'm going to show you later are done in the PBE functional, exchange correlation functional. And so we make further approximations, and so we no longer have an exact theory for any of the calculations we're going to do. But even the in-principle exact theory, the density function theory, it's only exact in the ground state. So you get things out of DFT that look very much like excited state properties, but they're not even in principle going to be exact. And these approximations we're making for the exchange correlation functional are very much like mean field or self-consistent field type of approximations. And so this makes excited states even worse than you might hope if you had the exact functional. And basically there are three approaches you might take to dealing with this problem, and the first one is to ignore it and hope that everything works okay. And that's often not so bad, and the important thing to notice is that this does tend to get trends correctly, but sometimes if you're interested in details, then it can be pretty bad. And the classic example, if you're a physicist, is the band structure of silicon. You get the gap between the conduction and the valence bands wrong by about 50%. In sort of most straightforward applications of density functional theory. A second approach that's very elegant is the time-dependent density functional theory, and introduce imaginary time, a bit like Meredith was talking about this morning with quantum Monte Carlo, and you can get excited states formally correct in this theory, although again you just have to do approximations to implement it. And the third approach, which I'm going to take, is very much more suck it and see. And it's often referred to as delta SCF, or difference of self-consistent fields approach. And basically what I'm trying to illustrate here is the energy of the excitation in this is you calculate the system in its true ground state, and then you move it into an excited state, and you impose a constraint on the system that it has to sit in this excited state over here, and then you calculate this state in the functional theory, and then you subtract the two energies. And it turns out this gives you a much better estimate of the excitation energy than just taking the Kohn-Sham eigenvalues and interpreting them as if they were eigenvalues in the Schrödinger equation. And empirically it's found that this is almost as accurate as doing time dependent much of the time. Okay. So on to the calculations. So that's really a health warning, and you should bear that in mind, all the excited state numbers I'm going to tell you in a minute. So these are a picture of some of the monomers that are involved, that are well known to be involved in melanin, and these are the HOMO wave functions calculated in DFT, just to they make most of the pictures really at the moment. And basically there are kind of three models in the literature about what's going on. So one is the oldest, is that there's a highly cross-linked extended heteropolymer that ends up giving you semiconductor functionality. The second model is that there are small aggregates that contain only 4 or 5 oligomers, and there's some specific structure of these which has important properties, and this model is still around, and this paper is from only last year, arguing that a particular kind of tetramer is dominant in the structure. And another thing that Paul argued yesterday is that we think that there's not really a structure, basically, and that disorder is actually the dominant effect you need in order to understand the properties. 2 minutes. Okay. So here's some numbers. So this is for a bunch of different possible monomers, and here's some that I didn't show you before. Don't worry about what the names are. What I want you to take away is that this being the most reliable set of numbers is that it's quite a large spread across different molecules. And if I go to dimers and start sticking dimers together, then again I see further spread, and there's more of these redshifted. And so if I take a whole bunch of dimers, actually there's 42 dimers in here, which is very Douglas Adams, I guess. And so what we've done here is we've put in an empirical temperature to determine the the different populations of dimers in this effective medium, and we've broadened all the peaks, and then we've averaged over the ensemble, and so as we vary the temperature, and you put this up, you see a lot. You see basically something that begins to emerge. It starts as you have an ensemble of these things to look very much like the absorption of melanin. And you shouldn't take the actual number of temperature too seriously, and there's a number of details that you would like to do better in this calculation, which I'm just going to sweep under the rug today. You can ask me about the nature of the growth. And it turns out when we look at it experimentally, if you take Dicker, it evolves actually quite slowly compared to other materials. So Dicker is one of these building blocks. And if you measure its absorption spectrum as a function of time, so this is the earliest time here, and you can see some quite distinct, this is the earliest time here, you see some quite distinct bands, and as you let it evolve as a function of time, these bands begin to go away and it smooths out, and so this peak is within about 20% of where it's predicted to be in the VFT calculations. And so, finally to draw my conclusions, the main point is that we've seen that yesterday the transport is highly sensitive to the humidity, and that seems to imply protonic conduction. And so this really brings the Longy-Higgins-McGinnis model of the broadband absorption arising because of a semiconductor band structure into question. And so what we're arguing, based partly on intuition and partly on these calculations, is that it's quite plausible that the broadband optical functionality can arise from a highly disordered system. And actually I think this is not really a very radical hypothesis. So as one organic chemist told me, every organic chemist knows that everything you synthesize is brown before you purify it. And so really, if nature can use this to its advantage to get something that's brown and will absorb sunlight, then it's going to be a very easy way to do it. And we believe that this is how the absorption of melanin arises. So thank you for your attention.
We'll skip questions till after Seth's done his half, and then we'll question you both.
Should have done this beforehand.
You okay?